Hi, good morning, everyone. Uh, Welcome to Big Data Analysis. Okay, so today we will discuss about regression. Can you hear me well? Yes. Okay. Uh, the slide is in Lentera, so you can follow this. And this is what we discussed in the last meeting. Okay, so we suppose we have this kind of data. Okay, so we would like to predict uh, the population in the year of 2005 and 2010. If we have data from 1980s until 2000. Yeah? So we have how many data? 1, 2, 3, 4, 5. 5 data of population in hundreds of thousand person. So a small town here. Of course, we have 5 data points, so we want to predict the next point. Okay. So uh, one way to do first is to plot this data. Okay, so here is the plot of the data, and it seems like based on this plot, we would like to have a straight line model would be the best fit. So, but you can see that there are many ways to do the straight line here. Okay, so which line is the best? Okay, and that best is actually depends on the criteria. Okay, what is the meaning of best? Its argument can be saying that uh, each person can have their own criteria to argue about what is best. Okay, so the common objective criteria of what is best is actually based on error. Okay, error in this case is the discrepancy between the model, okay, which is the prediction of the data, and the real data point. So we measure the error based on the say, suppose we have the model already. Okay, this is the line that we have as the model, and this is the data point. Okay, this star. Then the error is measured as the difference in the y direction. Okay, so in the vertical axis. So if the point is above the line, so we said it's positive. If the point is below the line, then it is negative. So the problem with this measurement is the sum of the error will be zero. Right? If the model is exactly in the middle, then the error will be zero. So in that case, we need to square that error. Okay, but by squaring the error, okay, actually we assume that the error is actually normally distributed with zero mean and constant variance. So this is the last time that we discussed. The red line is actually the best with the minimum sum square of error. Yeah. So now, instead of guessing, right? So we can also use this formula. So this morning we will practice this. Okay. Uh, Basically, the practice is how to read this formula and implement this formula into Excel. Yeah? So if you look at this formula, n is the number of data points. So we have 5 data points, so n is 5. Sigma xy, okay, is the multiplication of x and the y. So the data is x and y. Okay, and then sigma x means the sum of the x, and sigma y means the sum of y. And then we have also sigma x squared. That means for each x we square it. Okay. Here sigma x and then square here is mean you sum first the x and then you square. Okay. After that you can get the slope. Once you get the slope, you can also get the average of the y and average of the x, and then you can calculate the intercept. Once you calculate the intercept, you can calculate the prediction. This why we caret here is mean the prediction. Okay, so how to do? So first thing is to type this data into Excel. Okay, and then you use this formula to calculate the slope and the intercept. Okay, so let's do that. Okay, so I type here the data, the 5 data points, so 1980, 1985, 1990s, 1995, and 2000. So then the year represented by the X, and the population in here is the one that we want to predict, so this is the Y. Okay, so then you can calculate the sum of all the data points, and then the average of all the data points, right? And then I copy this, and remember this average, I put this name as X bar. Okay, so this one I keep name X bar underscore, and this one is the sum or the average of Y. So I put this as Y underscore, so Y bar. So the count, of course, you just put count, right? The count of the data is 5, right? So, okay, so then you start to compute the XY. That is simply multiply X multiplied by the Y, right? And then X square is just the X, you put square. Okay. Okay. So what happened is we copy all of this and get the sum. Okay. So I copy it here. Okay. So once we get the sum, okay, then we can start to use this formula of the slope here. So we have xy, this one. We have sum of the x here, sum of the y here. We have x squared here. We need to sum it. And okay, so we can calculate this slope. Huh? So this is n. So I put this n underscore so that you know the slope is basically the n. Okay, multiplied by the sum of xy. Which one? Okay, so this is the xy. So the sum of xy is this one minus the sum of x. The sum of x is this one multiplied by the sum of y. So this is the nominator, right? And put this divided by the denominator. So divided by n, again this one n, multiply by x squared, sigma of x squared is this one, right? Minus sigma of x, this one. This one is multiplied by itself, so square. And then you close it. Okay. So once you get the slope, okay, you can also get the intercept. So the formula for the intercept depends on the average of the y, this one, minus the slope, this one, multiplied by the average of the x. So, right. So once you get this slope and intercept, okay, now you can start to calculate the prediction. So this is prediction. Okay, so the prediction is simply based on this formula. Okay, so prediction is basically just the slope. Let me give name. This is the slope, and this one is the intercept. Okay, so the prediction is the same as the slope multiplied by the x here, okay, plus the intercept. Okay, so here is the prediction. So you can see this is 2.1, the prediction is 2.08. Oh, pretty good, right? The population should be 2.9, and then the prediction is 2.76. So pretty good, yeah, very close. Okay, so but let's calculate the error. So in that case, the error is equal to the prediction minus the population. Okay, and you can see here, if you take the sum, okay, it becomes 0, very small number. Exponent of minus 13, that very small number is equal to 0. You can see this is actually 0. So to minimize, what we want to minimize is the sum square of error. So I will put this as SSE. So to get this, we square of this error. Okay, and then we sum. We take the sum. Okay. So right. Once you take the sum, we can get what is called sum square of error, SE. Okay. We can also calculate the actual population here, y, minus the average, yeah, of the y. And then here we square it. Okay. And we calculate the sum. Okay. Why is that so? Because we want to calculate what is called the sum, the R square. Yeah? We want to calculate the R square. So R square is SSE divided by SST. So this is SST, yeah? Sum square of total. Okay. So in that case, we can calculate the R square. R square is just 1 minus SSE here divided by SST. Oh, there. So these three are the main result of this regression computation. So I put in this color. Okay. So up to here, is there any question? So you can start to practice and make it. After that, you show to me that you did it, and then you can claim that as your recitation. little. Yeah, so you make it very good, right?
Yes, sir.
Okay, so now you can predict 2005 and 2006, 2010. Yeah. How do you get prediction? So that one is a slope, yeah? Slope multiplied by this 2005, correct?
Yes.
And then and then plus the intercept. Yeah. Okay, okay. Yeah, that instead of value like that, you can refer to this
This one, sir.
slope and intercept. Yeah.
Mm.
Okay, very good, Karim. Anyone else want to share the screen?
Maybe I will try.
Hmm. Oh, okay, okay. So what you need to calculate is only the R square, or you did it already? Okay, excellent, Amira. Yeah. Okay. Yeah. Very good, very good. So you can now predict 2005 and 2010. Okay.
Yes.
Okay. Anyone else want to share the screen? So don't forget to claim your recitation. Every time you ask question, you give comments. Okay, you perform in the class, so you need to claim. Okay, so far only 6% claim. So uh, without the recitation, this is the grade that you set on your own, right? So without the recitation, I don't think you can get A. You know, even if you get very high score in all the exams or even the projects, recitation will be crucial for you. So you're probably wondering why I gave you this Excel exercise. Okay? My point is to calculate the SST and SSE, okay, so that you can calculate R squared. Why? Because later on you will calculate using nonlinear. Okay, for example, a different type of regression that you want, then you will start to wonder how I will get the R square, right? So the R square is still computed the same formula, you know, using the sum square of error and sum square of total. Okay, suppose you use different method to compute, okay, you are still using the same R square. Okay. So should I wait for you or we'll just do it? Okay, so I will share my screen again in this Excel. Okay, so earlier we have all this formula, so I will just remove this formula. Okay. Of course, Excel itself have a function, right? For example, this slope, you actually don't need to calculate this long computation. Okay, you can directly calculate slope. Right? So there is a function in Excel called slope. You just drag the y and the x, right? You will get exactly the same value. Okay, the same thing with intercept. You have a intercept in Excel, right? So you just put the Y and the X. You will also get the same result, exactly the same result, right? What is this? The R square. Is it correlation? Let's try if that is true. So correlation between this one and that one. No, it's different. So correlation is not the same as R square, okay? So that R square you cannot calculate using function, but you can use this. So you put the chart. Okay, so you put the chart here, and then you right click. Okay, and then add trend line. Right. So if this is linear, so you can just put the intercept, the equation, the equation and the R square there. Okay, then you get the same equation and the R square, yeah, using Excel. Right. So still another method using Excel. You can use data analysis menu here. Okay. And then you can start regression, select, okay, and then you have the Y and the X, right? And then don't forget, because I put the label in the beginning, so I put label, okay, and I will put all the graph here, there. So I got exactly the same value of intercept and slope, okay, and then I got the R square here. Yeah, so I'll just put this R square here, and then this is the 2 value here, and then you can also get this T statistics, okay, and the significant F. So these are the numbers that you need to consider. Okay, so many numbers, but these are the things that you need to consider. Okay, R square here represent the goodness of fit of this model, the whole things. Okay, the intercept is the intercept of the parameter, and the year here represent the slope. Yeah? And then if the significant value of the F is here, this must be bigger or smaller, less than, yeah, should be less than 0.05. Yeah? So this value must be less than 0.05, and then the T stat here must be larger than 1.96. Yeah? The absolute value of the T statistic must be larger than 1.96. Yeah? So, and then from the residual chart here, you basically can check whether this is a normal distributed or not. So these are the important points in regression. Okay, so yeah. Okay, so this is what you computed a while ago, right? And then from there you can calculate the prediction simply by inputting the X in here. Of course, the X in here is the year. So you just put 2005 in the year, you get the population of 2005. and then you input 2010 in the year. Here you can get the population of 2010, right? And modeling is actually an art and science, not just the science. So even if you have the formula, okay, you still need to guess. Okay, you still need to guess what model that you will use. So in this example, it's very clear that this model is linear. So how do you know? You plot first, right? And then you check the plot is practically linear. Okay, so don't forget to plot first, okay, to check the fitness. And after that, you can use the scientific way to examine the goodness of fit of your model. This is the formula available for simple linear regression. Okay, so how you get this formula? That's the question, right? To get this formula, we minimize the sum square of error using what is called least square method, right? So I'll give you a step in least square. First is to calculate the difference, okay, between the dependence and the model estimation, and then you square it, okay, and then you take the summation of all the data, okay. So this is the square of error basically, right? So after that, what you will do is to take this sum square of error, and then you take the partial derivative for each parameter and equate it to 0. Okay? So this is the example. Suppose I want to have a model of y equal bx without c, without intercept. Okay, so what I will do, I will set up the error here. Okay, and we know the y and we know the prediction, which is the bx or ax in here. I can put it here. Okay, then you put this here. Okay, and then you square it, right? And then you sum. After that, you take the first derivative, yeah? Because you have only one parameter, so this is not partial derivative, but the first derivative. So if you take this equal to 0, you have this formula for the slope. Okay, it is different, right, from the one that you just computed a while ago. Okay, so the derivation for this formula here you can check in my website, okay, in Refoledo. Okay, so you're supposed to practice this, okay, so that you can be able to answer your exam question. Okay, so this is the answer. You can just input the values, and then you can get the slope and the intercept. Yeah. Okay, so once you get those formulas and computing the slope and intercept as well as the R square and the T statistics, so how do you say that this is a good model or not, right? So this is called goodness of fit measure. So there are several numbers that you can use. First is the R square and the F statistic. This is useful to check whether your data is actually fit with the model. So, and then for each parameter, you use the T statistic. So this is the rule of thumb that we can use. The R square must be larger than 0.8, and then the T statistic must be larger than 1.96. And of course, you need to verify that there is some causal relationship, yeah, between the dependent variable and the independent variables. And then the sign for each parameter must be correct. Okay, so these are the criteria that we have a good regression model. my question to you, what happens if there is no causal relationship? And what will happen if the sign is not correct? Is there any idea? Example, there is no causal relationship if the dependent variable y is actually, for example, the flood, the amount of flood in Jakarta, and the dependent variables is actually the amount of traffic in Surabaya. Yeah, different cities, right? So there is no causal relationship between the two variables, but if you put into regression, they probably have certain good fit. Okay. Even if the regression said it is a good fit, does not mean it is a good model, yeah? Because there is no causal relationship between the variables. So in that case, you reject that model. Okay. The same thing. What will happen if the sign, okay, of certain parameters actually reverse? Okay. You must verify on your own. Okay. For example, if you increase this variable, what supposed to be the impact to the output? Yeah. If you increase or decrease the input, okay, what will be the impact to the output? So if the impact is actually known and it's wrong sign, then you probably make a wrong model. Okay, so modeling is not just science, you plug in the data into the formula. Okay, you're supposed to think whether this model is correct or not. You're supposed to interpret that model. You need to verify that model. Okay? Logically, they are correct or not. Okay. Otherwise, computer will do all the things. Okay? You just plug in the numbers into the computer and you get the result and you believe that result. And you are not human anymore. Right? So that is not true. Okay? You're supposed to interpret, you're supposed to verify. Okay? So in any data analysis, whether it's small data or big data, these logical things must be there. Okay? So if there is no causal relationship within the data, yes, you can put to the machine, okay, and it produces certain things. Okay, so correlation can be very big, right? And R square can be very big. F test can be very nice, okay, less than 0.05, and the t test pass. But the interpretation is wrong. Then this is not good model. Okay, so don't just rely on the computer. That's my point. Okay. Next. Let's come back to the slide again. Yeah. So, the overall fit, okay, it will compare several models. It's useful to compare several models, okay, and it will determine whether the model is correctly fit the variation in the data. Don't forget what is done is actually just to fit the variation in the data, okay, and t-test is useful to remove the redundant variables, okay, and to remove also the weak variables that probably exist by chance. Okay, so later I will show you certain things. So the R square or sometimes called coefficient of determination. Okay, this is the formula. It's just a proportion of variation explained by the baseline model. Okay, it depends on the sum square of error and the sum square of difference around the mean, right? That is SST. Okay, so you already know that we computed SST by the data minus the mean of that data of the dependent variables. Okay? So in that case, we call this total variation. Okay, so we get this value for the R square, right? So, but if you have multiple linear regression, okay, so the more variable that you include in that multiple linear regression, the R square will become larger. Okay, so in that case, a kind of cheating, right? So you can put a lot of variables, then the more variable that you put, then the R square will become larger. The same thing, if your number of data is very big, the R square will become larger. So in that case, R square is actually dangerous to be used. Okay? So we need to adjust that. Okay? So to adjust the R square, so we put this R square adjustment. So in that case, it's not based on the sum square of error, but we use as mean square of error. The same thing with the mean square of total. Okay, so this is the new theory that, look, we don't use the R square for multiple linear regression. For simple linear regression is fine, but for multiple linear regression with a lot of variables, don't use R square. Yeah? You use adjusted R square. So you can see in Excel a while ago, right? So there is a multiple R, and we have also adjusted R square. So here, right? So this is based on the mean square of error and mean square of total. Okay? If you have a multiple linear regression, we don't use the R square, but you use the adjusted R square. That's the point. Okay. Next. Yeah, the same thing, yeah. So the R square or the adjusted R square must be higher than 0.8. Okay? So if your R square is less than 0.5, then you probably want to try other model rather than linear model. Okay. So another measure of the whole goodness of fit is standard error. So it's basically the square root of MSE. Yeah? What is that? The SSE divided by the N minus Q. N is the number of sample, Q is the number of variables, or the number of coefficient, because variable here including the intercept. Okay, so another measure is to use F statistics. So this is the formula. Yeah, we use MSR, which is basically SST minus SSE divided by Q minus 1. Again, the Q is the number of variables. Okay, and then you can compare it to the F table, and basically you can get a significant level. If less than 0.05, then you can say this is best fit. Right. So these are a few indices that you can use to check whether the linear regression or simple linear regression is good or not. Right? So this is the computation of the F value. Okay. We call this ANOVA. Okay. ANOVA table. Analysis of variance. ANOVA is analysis of variance. Okay, so to compute the t statistic, that is to compute for each parameter. That parameter include the variables or the intercept. Okay, so this is to compute the t value for each variable and the intercept. Okay. Anyway, you already have the software that you can compute. This is just a formula. Suppose you want to create your own software, so you can use this formula. Rarely happen. And the absolute value of the t statistic as a parameter must be less than it must be larger than 1.96. So if less than 1.96, that means the error cannot be explained within 0.5, within 5%. Okay, so this is the summary. Okay, the R square must be larger than 0.8, the significant F must be smaller than 0.05, and the absolute value of the t statistic must be larger than 1.96. Yeah. Okay, so with that, okay, this how you interpret the table from regression in Excel. Okay, I already explained to you the function in data analysis and the trend analysis in Excel. Okay. Next is to compute. We also have done about manual computation, right? So next one is actually to compute into matrix. So these are just a step. I just skip it. Okay, so be very careful. Okay, when you match your data with polynomial model, okay, because polynomial can be very sensitive, especially if this is a high degree, okay, and it can lead to incorrect prediction. Okay. Why this is overfit? Okay? The reason is because polynomial tend to be overfit. You see, it will in high degree of polynomial, it will pass through all the points. Okay, so it is very good to interpolate the model, but it's very bad for extrapolation. Okay, so some model, okay, some non-linear model can be transformed into linear model. Okay, so this is the a few examples of non-linear model that you can transform into linear model. So say y equal a times b exponent x. Okay, a and b here are numbers. Okay, y and x are the variables. Then you can transform by taking the log y. Okay, so if you take the log y, the x remain x, then you will get log y equal to log a plus x times log b. Then this is a linear model. The same thing if you have this model of y equal a times x exponent b. Can you see the difference? Okay. This one is a b exponent x. This is a x exponent b. In this case, again, you use double log. Yeah? So you use double log in here. This is supposed to be log x and this is log y. Okay, and if you have this kind of non-linear model, okay, you can also transform into linear model by using y 1 over y. Okay. So this is the review of power rule. Okay, so if you have the product, okay, E is the number, and P and Q is the exponents, right? Then if you have the same base, you can sum. Okay, if you have the same base multiply, you can sum. If you have division, you can minus. If your exponent is the same as multiplication. Okay, the same thing. This is the logarithm of exponent of p, e exponent p multiplied by e exponent q. So exactly you take this ln of this, ln of e is equal to this p plus q, right? And so on. So these are the review for the power rules. Okay, and this is the review for logarithmic rules. Right? From the sum, okay, of log x plus y, you can put it together. Okay? The same thing if you have log x minus log y, you have log x divided by y. Okay? Log of the root will become the inverse. Okay? Log of the product of a log, you can put it as exponent here. The p will go to the exponent. Why we review this? Because we are going to use this to derive. Okay. So some simple nonlinear model can be transformed into linear model. So be careful here. The goodness of it is the r square and the t statistic will not change by the transformation. Okay. So let's try some of this. Or which one you want to try? Okay, so let's try this a b exponent x. This one. Let's try this a b exponent x. Okay, or this one. This one. Yeah. So a y equal to a times b exponent x. Okay, let's try that. Okay, so that you will understand. So I will create a whiteboard. Yeah. What we have. Our model is y. Okay, y equal to a what's this? X exponent p. Yeah, x exponent p. Okay, small x. Small x exponent p. So this is our model. Okay. What we will do? We want to transform this into linear model. So clearly this is non-linear. So what you will do is to take the log. Okay. So log of y, okay, equal to log of a x exponent p. Right. So then you have logs of y. Okay, my log is so bad. Equal to, what is this? You get the log of a plus b log x, isn't it? Right? So then I can give name. I can give a new name. This one is a capital Y equal to, this one I could put this as alpha plus b still b, and then this one I will put as capital X. So I got a new model which is a linear. Okay. So once I have this, okay, what I will do is, don't forget, okay, alpha, okay, equal to log a. Okay. Right. In that case, a equal to, so depending on your base of the log, for example, if the base of the log is 10, then you have 10 exponent alpha. Okay. this clear or not? So let's try that, okay, by example. Okay, so suppose we have this data, okay, and find the regression power curve logarithmic of square root. Yeah? Okay, so I will create a new sheet in my Excel. Oh, well. Okay, I will create a new sheet. So I have X and Y here. All right, and then what I will do is to type the value. Okay, so I have 7, 14, 24, 30, 45, and 57. Here I have 24, 34, 45, 50, 61, and 61. Wait, I have left and 69. Is that correct? Okay. So I want to first thing I do is to plot, right? First thing I do is to plot this. Okay, or I can just use the change the type. Right. So this is clearly non-linear, right? Clearly non-linear. So in that case, I need to find out what is this. Okay. So let's do it manually. So what I will do is to get this model y equal to a x exponent b, right? So we want to get y equal to a times x exponent b. And multiply here, so like this. Okay. So how are you going to get the a and b? That's the question, right? Okay. So what you will do, you will get the log y, right? Log of the y equal to log of a plus b multiplied by log of x, right? So in that case, you have the y equal probably alpha plus b multiplied by capital X. Okay, so what I will do is I get this log y and I get the log x, right? Based on that derivation here, right? So you get this log y and log x, and we know this is the capital Y and this is the capital X, right? So there. So you can put log any base that you want. So I will just use the log 10, right? So of the y, and this is the log 10 base of x. Okay. So this is our new data. Clearly this is non-linear, but this must be linear. So you can check here. Okay, let's plot it. You see, it's linear, right? So when you transform the data, okay, into a two log in here, you can see that the model become linear. Can you see it or not? Okay. So then once you have this transform data, you can calculate the slope and the intercept. So I can get the slope and the intercept, right? What you will use? Of course, the new. Yeah? Remember, the slope and intercept here is working only for the linear model, yeah? Not for the non-linear. So I get the slope here, slope. Slope of y, oops, what happened? Slope of this y and the x, right? The same thing with the intercept. The intercept of this y and this x. So what is this? This slope is the same as b, huh? And this intercept is the same as alpha, huh? Right? This is the same as alpha. So, but you don't want alpha. What you want is actually, your model is this, right? Y equal a multiplied by x exponent p. I got the p, but I don't get alpha yet. So how do you get alpha? Remember, alpha is the same as log a, right? So in that case, a equal to 10 exponent of alpha, right? So then I can calculate here a is equal to 10 exponent of this alpha. Okay, I got this value here and I got this value here. Then of course I can use already. Yeah? So I can get the prediction. Okay, I can get the prediction. Okay, which is what? The a, okay, multiplied by the x. This is the x here. Okay, exponent the p. Exponent p here. Okay. So this is the exponent of p. So I need to put them under a here. Again, I put them with double. Huh? So this is the prediction. Okay. Is there any question? Can you do it on your own? If you do it, then you can share your screen.
Part, sir.
With
Maybe I can share screen,
yeah, you can share your screen.
Sir.
Okay, already got that.
Yes, this one, sir. I think I lost here.
This one is finished. You just copy down.
Oh, this one is correct, sir.
Oh, wait a minute. Can I see? Your value is the same, 0 point. But why the prediction is different?
I don't know, sir.
Wait. F12. Where is F12?
F12. Oh, this one. This one.
No, not F. Yeah. A. That's correct. So A multiplied by
A multiply by.
not T. Not T3 is a X, right? Your
Oh, yes, sir.
so this is P3.
Yes.
P.
Oh, P. This.
Correct. Yeah.
Oh,
Okay.
okay, sir.
So you get that.
Yes.
Okay. So after this, you can start to plot if you want. This X, Y, B and C, column B and C, you can plot, and then you can use the power curve in Excel. Can you plot?
Good, sir.
Yeah,
This one.
correct.
This one.
So you plot that. Okay. Scatter
This.
the scatter plot without any line. Okay. Good.
Yes.
Click that. And then now you check any point there, and then right click. Right click and then trend line. Add trend line.
This one.
Correct. So now, okay, you check the trend line now. Wait, you can change the trend line, right?
Wait, sir. Wait.
Yeah,
Uh,
there in the right side here, you can check if your trend line is
wait. In the right side. Where, sir?
no. Again, you do it again.
Okay.
Delete the trend line first.
Delete the chart or not, sir?
Just there.
Wait. Like this.
Okay,
Then
and then you start with the trend line again.
start with the trend line.
Okay. Right click. Yeah.
Right click.
No, click one of these points, and then you do a right click.
Oh, yes.
There,
Then this.
add trend line. Okay. There, if you see here, there is a power curve here.
Oh, this one.
Yes, and then go down,
Put down.
and then you can display the equation on chart and the R square as well. Go down again. There,
Yes.
you get that. Oh, you get exactly the same, right? You see this,
Yes.
the slope, and A and B, you get exactly the same.
Yes.
Right. So meaning your computation is correct. Yeah.
Okay, sir.
Yeah.
Yes.
Yes. Excellent. Okay. So now using the same data, can you try to compute the a different model? Okay. Instead of power curve, for example, you can try using logarithmic curve or using exponential curve. Okay, let's try exponential curve. What will happen?
Exponential.
Yes. You calculate using exponential curve, so the, the model is y equal to a times b exponent x. It's not x exponent b, but b exponent x. So what will happen? Okay, So I will share my whiteboard again. So this is what happens when you have y, okay, equal a x exponent b, right? But now we will change this, okay? We will change this model. We will have, I will have an eraser here. Okay. So what I will have a new model with this b, b exponent x. Okay. What we will do. Okay. So here, of course, we will change this. Right? So okay, let me delete this part. So you have a new model here, which is b exponent x, right? If you take log both sides, you get log y equal to log a times b exponent x. So what you will have? You will have log y again, okay, equal to what you will get? You will get log a plus log of b exponent x, right? So you will get, in that case, what you will do? So that one is equal to log a again plus x times log b, right? Right? Oh, so I have log y here, log y equal to log a times plus x times log b. Oh, I will create a new variable, capital Y equal to, again this is alpha, plus x, still the same x, but now here I call this beta. Oh, sorry. Let's call this beta. Okay, what is alpha? The alpha is log a, right? And beta is basically log b. Yeah. So then if you want to use this, what you will do? The x in here remains still the same x, right? Can you see? Remains still the same x. So in that case, you don't log the x. You only log the y. Okay. Once you get that, you will get alpha and beta. Okay. And then what you will do? A equal to 10 exponent alpha. Here, b equal to 10 exponent beta. Yeah. Okay, so you need to derive in order to know what to do. Okay, so let's do that, the same thing here in our Excel. Okay, so I will use exactly the same data. Okay, so I will use the same data. I'll copy down here. Right, I will just copy the same data. So remember, we have our new model. Okay, is what? Our new model is y equal to a times b exponent x. Okay, so this is our new model. So then we know that this is log y, okay, equal to log a plus x multiplied by log p, right? So that means y equal alpha plus x multiplied by beta. Okay, so x still the same x, okay, only the y now become capital Y, right? So the x still remain x. Now I need to get the slope, right? So what I will get the slopes? The slope is from the y, in this case the y is the log y, and then the x is actually still the same x, yeah? Not log x, yeah? This is the same x, okay? So this is the slope, and the intercept, now the same thing using the intercept function, right? The y is the log y, but be careful, the x is not the log x, but the actual x. Okay, so once you get this slope and intercept, what you will do, of course, I will get this slope and intercept is what? This slope is actually, okay, the same as, what is this? The slope. This slope is actually beta, isn't it? Yeah? This intercept is actually the same as alpha. Huh? We know that. From how do we know? Here. We just put it here. Yeah? This is the derivation. Right. So if we know this, what we want to get? We want to get A and B. We don't want to get alpha and beta, right? Our model is, so I want to get A and B. So how to get the A? A is actually 10, yeah, exponent to the alpha. Oh, this is alpha. And then how about B? B is actually 10, exponent to beta. Okay, so I get A and B, so I can get the prediction, right? So this is the prediction. With this y caret, okay, is equal to what? A times B, exponent x, right? That is what we want. So then I have A, here A, multiplied by B, and then exponent of x. X is the actual x. Okay. So these two, A and B, are constant, so I'll put value here. Okay. So you get the prediction. Okay. So up to here, can you do it? You want to share your screen?
Sure, I'll try. Is it like this?
Okay, so you get, oh, a little bit different. Do you use the same data? Oh, you use different data, that's why. If you want to test, so you can test, okay, whether your computation is correct or not, right? So in this case, you can use this x and y, and then you plot. Okay, you plot using this original x and y. Using this data, can you plot this data? Insert Oh, no, only the X and Y. You, okay, go back again. Maybe faster if you go back. Only this one. You highlight this first. And then you plot. There. Is it? Okay. Your value is a little bit difficult. uh, 43. Okay, so you created a random value, right? In this case.
Yes, sir. I use random data.
Okay. So this is okay. Anyway, so actually, if you use this random data, this model is not correct, right? This model is incorrect for this random data.
So we need to use the exact data.
You create a model based on the plot, but this plot is clearly not power or exponent. Okay, nevertheless, let's try. Okay, just for the sake of computation. So let's try. So what you will do is you click here and then you right click there. You do a right click there. No, you click one of the data first and then you right click. No. Right there, you have an up trend line. Can you see? Okay, you select add trend line here. Okay, and you select exponential there. Okay, and then display equation and display the R square on chart. Okay, and then when you close that, you can see the equation and the R square. Yeah, the R square is clearly very poor, right, for this data, but the computation is correct. 48 you get, and 0.9, no, this 0.9 is incorrect in that case. 48 is correct.
I see, sir. Okay.
Okay?
I'll try to revise it, sir.
Yes. So there is something wrong with the computation of the P. Okay, anyone else want to share screen? Okay. So you're using which one?
Yes, sir. This one is the one that before you
Okay, so this
explain.
is the earlier. This is the double log or the one log? Okay.
This one, sir, the formula. I use this one.
Okay,
Just
you use that
the
one.
one that you just explained. Yes.
Okay. So in that case, only the y have log, the x no log, right? Okay, and then you get, let me check the value, 24 and 101. Yeah, I think I get exactly the same as yours. Yeah? Right. So if you want to check the correctness of that, so you can also plot. Okay, so if you plot x and log y, you will exactly get a linear model. Where is your plot? Say you want to plot x and log y. Okay, try to plot x and y first so that you will. Okay, plot insert. Base value, okay. And if you plot that, it will become linear model. Almost linear. Is it? Oh. So if you plot X and Y, you can also check whether your computation is correct. The original X and Y. Okay, and scatter plot. Okay, and then you right click there. No, select one of the points and then you do a right click. Right, there's an arc trend line there. And this is exponential, so you select exponential. And then display equation on chart and the R square. On the R square. Right, so you see this is, okay, you can close that on the right side. So is this correct or not? You can check A and B is correct. Right, I mean, in the equation, you can check that is 24, okay, exponent of 1 point something. Yes. Now, of course, you can select many, for the same data, okay, you can select many different type of non-linear transformation, right? So which one is the best? Okay, the one, of course, the one that is best is the one that is closest, yeah, to your data. In that case, the R square will be the highest. Okay, so you select among all these possible curve that you have. So which one have the highest R square? Okay, so you can compare different model, right? So how do you compare? You compare the R square. Okay, the one that has the highest, so you can select linear, exponential, logarithmic, okay, and so on. Okay, and the highest R square, that is the one that you use. Is it clear or not? Yeah. So the one in the slide, if you look at the transformation in the slide, okay, I include a square root and reciprocal, which is not in the Excel function, right? That means you can also calculate different transformation, okay, which is not exist in Excel, so you need to calculate manually. Okay. Is this clear or not? Okay, so I give you example. Okay, for the same data a while ago, say suppose your model is y equal to a plus b squared of x. Okay, so of course there is no submodel in Excel, so then you can transform. So the y equal to a plus b squared of x, or squared of x is now become capital X here. Okay, that means only the x that you transform. So x and y, and then you transform square root of x. Then you calculate the slope and the intercept. So the slope still b, the intercept still a, right? So, okay, and then you can do the prediction. Same thing. So then how to calculate the R square? To calculate the R square, you need to calculate the SSE and SST. So because Excel will not provide for you, so you need to calculate manually. Okay, it's the same thing if you have harmonic, something like this, or a different reciprocal model, okay, a square of harmonic, for example. So try to say if you have this kind of data, for example, okay, and you plot it, okay, so probably you will get exponential model will be the answer. Okay, so before I go to the matrix computation, is there any question? So what did you learn today? Anyone want to share screen?
Sir, I already revised my Excel, sir. Shall I share screen?
Yes, please. Okay, so you get the, okay, very good. So you get exactly the same, right?
Okay, sir.
Okay, so you get the result that you can calculate. Okay, so with this, practically you can create your own model and then you can transform it into a linear model, and then you can also do the computation. Okay, so is there any question so far? Anything to discuss? If not, I will stop for a while. So let's come back. Have you learned about matrix before? You know how to multiply matrix and take the inverse of matrix. Yes, no. Can I cut?
Sir,
What? What, Lindsay?
forget.
You forgot what you already learned, right?
I think so.
Okay, that is fine. So, I will explain in the next moment, okay, how we will solve regression, okay, using matrix. Okay, so you can also follow in the slide. So first thing first, why I want to show you computing regression using matrix, because this is the most powerful method, right? So using matrix, you can actually create any kind of regression, linear, non-linear, okay, including the classification, multiple linear regression, in the same formula. You don't need to change the formula. Okay? You only need to consider the size of the matrix. If you use Python, for example, you use the same formula, you can run it for different size. Okay, but in Excel, you need to consider the size of the matrix. Okay, and the same formula you can reuse for a different model. That is the power of matrix computation here. Okay, so for example, first I will explain to you, we can use exactly the same data that we used a while ago. Okay, so we use the simple linear regression here first. Okay, so what will happen if we have like this? Suppose this is our linear model. So say I have data, right? The data is x1, x2 until xn. Okay, and then this is the slope m, and then c is the intercept. Okay? And our dependent data is y1, y2 until yn. So for each data, so I can say that m multiplied by x1 plus c equal to y1. Right? M equal multiplied by x2, this is the second data, the second row of the data, plus c equal to y2, and so on. Right? This is supposed to be like this. So then we can use this into a matrix form. Right? So what is the matrix form? This is the x, okay, and then plus c multiplied by 1. Okay? So the constant c multiplied by 1, okay, equal to the y. This is the y here. Okay, so in matrix form, I will have a matrix here. This is the matrix of the data, and then multiply by vector of a parameter m and c, okay? And then again this is the data of the output, the y. So this matrix, I call this A. Of course, consists of x and 1, right? So, and then now I have a system equation A times P equal Y. Yeah, P is equal to MC, and then Y is Y1 until Yn. So in that case, you have a system equation A times P equal Y. So this is a regression equation. Okay. As simple as this. Okay. So the question is how I will get the P. Right? This is what we want to get, right? Given the matrix A and vector Y. Okay. So the problem happened because A is not a square matrix. So because it's not square matrix, there is no inverse, right? So in that case, the trick is to multiply the matrix with its transpose. Yeah. So this matrix A here, okay, multiply by its transpose. Okay. So because this is multiplied by the transpose, I get also multiply on the right hand side. Okay. And then after I get this multiplication with the transpose here, of course, matrix multiplied by its transpose become a square matrix, right? So then this matrix alone, I can find the inverse. So this is the inverse of that. Okay. And because on the right, on the left hand side, I multiply by the inverse, then I copy this inverse on the right hand side. Okay. And a matrix multiplied by its inverse is just identity matrix. So this is basically no more. So become P. And here it is. We have this. It looks like very long, but this is actually, we can simplify into one matrix. Nah? So A transpose multiplied by A, and then inverse times A transpose, that is called left generalized inverse. So the solution is this. Yeah? So if I put L equal to this value, then this is called a generalized inverse. So P is just L times Y. Is it clear or not? Is there any question? So I will put in the whiteboard again so that it become clearer to you. Okay, so I have A times B equal Y, right? So the problem happened because A is not square matrix. So if not square matrix, I will multiply by its transpose. So A transpose, okay, times A, I will copy by B equal to, because on the left hand side I multiply by A transpose, on the right hand side I multiply by the same thing, right? And then what happened? So I put this together, okay? So because I can put this together, I can take the inverse of that, right? So A transpose times A, I make the inverse, and then I just copy this. I transpose times A times B equal, of course, on the right hand side, I need to copy this, right? So I have A transpose times A inverse. Now I copy this, A transpose times Y. But this one is basically identity matrix, right? So I get B. So P equal to, this one I will call this L times Y. Oh, so now become very easy, but be careful, L is actually A transpose times A inverse multiplied by A transpose. So you don't forget this one. Okay. So what I will do is use this to compute. Okay, let's practice this to compute. Do you want to practice the? Let's practice the same data that we have earlier. The population data. Okay, so I will share my screen to you. This is the population data. I will copy this, and then I create a new sheet. Okay. So we know that this result is 0.136 and negative 267.2, right? Okay. So let's calculate this using matrix. So what I will do, I will create a matrix A, right? I will create a matrix A, so I will call this MA. Okay. So MA consists of this X and 1. Okay. So MA is equal to this X and 1. So this is the input that we want. Put here. And then I have the vector Y. Okay, so vector Y, which is just the population here. So I will put this as our input again. So this is V vector Y. Okay, and this is our matrix A, MA. Right? So, what is the size of this matrix A? The size is 5 by 2, right? Okay, what is the size of this vector Y? Is 5 by 1. Okay. In matrix, size matter. Okay. So what I will do, I will multiply MA with its transpose, right? So remember our formula a while ago. To get the left generalized inverse, I need to multiply by transpose by A. Okay, so I will multiply A transpose, okay, multiply by A, right? So what I will do, I will multiply M mult, okay, of A transpose, so transpose of what? Transpose of MA, and then multiply by MA again. Okay. So if you do like this, it will become value, right? So you need to know the size. If MA is 5 by 2, so M transpose is 2 by 5. Okay, so let me make an M transpose first. A transpose, I will put it here. So A transpose supposed to have size of 2 by 5. Okay, so I will put it here. Transpose of A. The size is 2 by 5, so something like this. So first you need to put 2 by 5, you highlight, okay, and then you press Shift Control Enter together. Oh, press F2, Shift Control Enter together. There. Okay. So again, I will write here F2 function key. Okay, and then Shift plus Control plus Enter. Together. So A transpose is 2 by 5, and we know that if you have A size A comma B, okay, multiply by B, must be size of B comma C, okay, it will become C size A comma C. So matrix multiplication, okay, the number of column must be the same as the number of rows in the second product, second element. Okay, so we have 2 by 5 multiplied by 5 by 2. So in that case, I will have size of what? 2 by 2, right? So there. Okay, you highlight 2 by 2, F2, Shift Control Enter. There. I got the result. Okay, so if you get this result, what is this? If you compare, so 1988 or 19800, what is that? That is the square, yeah, sum square of x square, yeah? Sum of x square, and then what is this? 9950. That one is the sum of x, right? So exactly the same. Okay, so A transpose times A is basically the sum of x square and the sum of x, and then this is n. 5 is n. Okay, so I need to get the left generalized inverse, which is the inverse, right? The inverse of what? The inverse of A transpose multiplied by A, okay, multiply again by A transpose. Yeah? So I need to get left generalized inverse. So first I need to inverse this one. So I need to take the inverse. I will put here inverse. Okay, so let me copy this first here. This one is the A transpose times A. Right. So now I need to get the inverse of A transpose by A. So let me put it here. So to get the inverse, so I will just put M inverse. Okay. I already calculated A transpose by A. So I just put the array. Okay. Most important part is you know the size, yeah? Because the inverse of a square must be the same square. So this is also 2 by 2. Okay. So press F2 and then Shift Control Enter. There, you get the inverse. And then you need to multiply that using to get the L. Yeah? What is the size of L? This is 2 by 2 multiplied by A transpose is actually 2 by 5. So I have 2 by 2, right? And then multiply with 2 by 5. So equal 2 by 5. Okay, so the L is 2 by 5, so I need to get the L here. Oh, I will just copy that. So L is just here. So I already calculated the inverse, so I just need to multiply and mode again of this inverse with the A transpose. Right? And I already know the size is 2 by 5, so 2 by 5. There, you highlight first 2 by 5, and then press F2, and then Shift Control Enter. There, I got this L. I got this matrix L. Now, if I want to get matrix B, right? To get matrix B, which is the parameter that we want, okay? Remember, B is just what? B is L multiplied by Y, right? So in that case, M mole of L, this one is L, multiplied by this Y. Okay. So what is the size of L? L is 2 by 5, and then by 5, and then 5 by 1, right? So B in that case is equal to 2 by 1, right? Okay, so I need to press F2, Shift Control Enter. Oh, I got that. What is this? This is exactly the same as earlier. This is the slope and the intercept, right? Okay, this is the slope and the intercept. Wow, we got the result. Exactly the same, right? So if you did it, please share your screen.
Sir, I'm sorry, I cannot follow up. I only follow until this one, sir.
Okay, so let's do it. Okay, so you
Yes.
A transpose. Okay, okay. So can you write down here, Karin, what is the formula? Oh, you got that formula. Okay, good. So our goal is to get the L and P eventually, right? So first you need to get the L. Okay, for your case, do you want to get directly L or you want to get one by one like what I'm doing?
Up to you, sir.
Oh, it's up to you. Okay, let's get the L directly, yeah, so that there is a variation in the recording. So, okay, let's. The most important part here is the size of the L. Yeah? The size of the L. A. What is the size of A? The size of A is 5(2), right? Correct? 5 rows and 2 columns. Right, yeah? So, and then A transpose is 2, 5. Yeah? 2 rows and 5 columns, right? So, in that case, A transpose times A will be 2, 2, right? Okay, and then the inverse will be the same, 2, 2. And then multiplying the inverse with the A transpose will become 2, 5 again. So L, the size of L will be 2, 5. Okay, 2 by 5. Okay, multiply by 5. Okay, okay, let's do that. So let's do it together. So can you put directly? You want to put directly? Or you want to do it by one? Let's do it by directly, yeah. So did you give a name for MA? Okay, can you keep name that? A underscore or MA, yeah, okay, MA. Enter. Okay, then, if you want to multiply directly, what you will do? You will multiply M mult equal M mult Karen, you can create equal sign M mult. Yes, that one. M mult of what? M mult of the inverse. So then M inverse. M. No. You just type M inverse. M inverse. M. Yes, M inverse of M mult again of transpose. Yeah, okay, you can put that. Hmm? Comma. Okay, transpose of A, MA. Close it. Close parenthesis. Comma. A, MA again. MA. Close it. And then you close again. One more. Comma. Transpose MA. And then close it and close it one more. Okay, enter. Oh, you get the L directly. Okay. And then you can now calculate the B. B is size of 2 by 1. Okay. Then P equal to L times Y. So equal M mole of L, comma, that Y, the population, or that Vy is the same. Close it. Okay. And, oh, you got it. Super. Okay. Excellent, Karen. So anyone else? Is it clear or not?
Yes, sir. Thank you.
So you can calculate directly, okay? Using based on that formula, you can calculate directly. But remember, you need to get the size correctly. Okay. Again, why we are doing using matrix? Okay, because the same formula, okay, L equal this one, and P equal L times Y, okay, the same formula will be used for a simple linear regression, for multiple linear regression, or polynomial regression, including the classification here. Okay, so the same formula. The only difference now is to create the matrix A later, and the factor P. Okay, that will be different. Okay. This is what we just did a while ago. So you have the X and Y, year and population. Then you form that matrix A, okay, and then you can get the transpose. You can get the A times A transpose times A, and then the inverse, and then you calculate the L. L is the general inverse, and then you multiply with the population Y. You get the P. In this case, the slope and the intercept. Yeah. Okay. You just practiced a while ago. Now, this is what you need to do. Sorry. Oh, class need to be ended by 10:30. Oh, okay. Okay then. So, this will become your assignment in that case. The class is interrupted. Okay, so this will become your assignment. Sorry, I did not check the time. Okay, so you use matrix to compute this. I'll post it. So then see you next week.
Okay, sir.
Okay, sir.
Thank you.
Okay.
Thank you, sir.
Thank you, sir.
Okay. So Josephine will be the one who put the time, right?
Sir.
Absent.
Okay.